Welcome and greetings from Boulder, Colorado in the States. I'm Stephen Voran at the Institute for Telecommunication Sciences. I appreciate your interest in this work, and I want to thank the QUOMEX 2021 organizers for making it possible for us to have these presentations in spite of the pandemic. The paper I'm presenting is Full Reference and No Reference, Objective Evaluation of Deep Neural Network Speech. Deep neural network speech is speech, of course, produced by deep neural networks, and they need some input. The scenario I'm looking at here is where they have what we might call conditioning input, which comes from a speech encoder of some sort. So human speech goes into the encoder, it produces some information at a low rate that allows a DNN to produce speech, which sounds an awful lot like that original speech. We can evaluate how much it sounds like the original speech using subjective testing, or with no reference objective tests, or with full reference objective tests. And I am very grateful to Jan Skoglund from Google, who has shared with us some databases of reference speech, test speech, and subjective scores that go along with them. And without this data, this work that you're about to see would have not been possible. Back to why this work, there are anecdotes regarding the tools that we have for measuring speech quality from DNN speech. One says Polka did not reflect informal listening impressions in the case of WaveNet DNN speech, and it was dramatic underestimation. There are numerous other published anecdotes and anecdotes heard at conference that make it clear that our full reference measurement tools simply don't work on DNN speech. I haven't found anything on our no reference tools. At the very last QUOMEX, a very specific study on this topic, documented more numerically in the case of PESC and several DNN coders that indeed there is a serious underestimation problem. We would like to have reliable automated measurements for DNN speech. They're very useful, and in fact one could imagine a situation where estimators are placed in an adversarial position with DNN speech generators so that both of them get better at doing their jobs. The data Jan provided is from 5 tests which cover corporately 32 conditions. 14 of them are DNN speech generation sources, and the other 18 are conventional speech conditions. They're rated on a subjective quality scale, a 100-point scale, motivated by the mush scale. I applied 13 estimators. 8 of them are full reference and 5 are no reference. 9 of these are speech quality estimators and 4 of these are speech intelligibility estimators. They are listed here in the chart. Certainly I have applied some of these out of their intended scope, but I applied all estimators to all conditions for uniformity and for breadth. In every case, I mapped the estimator outputs using a second order relation to something I'm calling M hat, which is an approximation of the subjective value M for Mushra. I did these fits initially using just the conventional or non-DNN conditions. Here are some example results. Scatter plots of the subjective scores versus the objective scores, Polka, Wideband, PESC, and Visqual. Over here, some no reference ones. Of course, the non-DNN conditions, the black ones that were used in the fit, are falling nicely on the line y equals x, but it's quite clear that over here on the full reference side, the DNN conditions, the blue ones, are grossly underestimated, and on the full reference side, they're grossly underestimated. On the no reference side, they're overestimated. In addition, you can see things like a trained test pair here, which have very similar subjective scores, indicating some good robustness and large difference in the objective score. Now, if we do the fitting on all the data, these pictures will shift, of course, but the underlying issue does not change. And these examples are borne out across all of the estimators that we have. Mean error here, RMS error here, and the estimators shown this way. So this is an indication of that underestimation by the full reference estimators, and here the overestimation by the no reference estimators. If we look at RMS error, we see still that the DNN conditions have a much greater RMS error than the non-DNN conditions. I also did the fit on all of the data, and of course what happens is we share the error here between the two categories, but the underlying issue does not go away, and the over-under trend does not go away. The error here, of course, is also shared when we do the fit on all the data. So consistent over-under estimation. We can, in fact, take a full reference and a no reference and average them to get what I'm calling estimator number 14, which has great performance because these errors are essentially canceling out. This is a pragmatic solution. It's not particularly pleasing. It's a full reference estimator with maybe more complexity than one would like. I argue that if we had more data, we could train our no reference estimators for better results on the DNN sources. I'm going to note that our quality and intelligibility estimators had not very different performance for this data, and also our full reference and no reference estimators had similar performance. But the crux of this then is the question, why do the full reference estimators underestimate DNN speech? The first thing I want to make clear is that this is not a failure. The DNN speech is, in fact, out of scope. Full reference estimators, indeed, they do seek to agree with subjective scores in all cases, right? Because they model hearing and judgment. But this has to be recognized as an incremental process. An ideal estimator would fully embody everything that humans do and would work for all technologies. But in reality, practical estimators contain sufficient modeling to cover existing telecom technologies. And when new technologies come on board and they bring new classes of impairments, estimators may fail. This then motivates us to do additional modeling or more refined modeling so that our models are complete enough to cover everything out there that we need to measure. And there's historical examples of this cycle. Just for example, when we went from circuit switch to packet switched transport, new impairments came up, new tools had to be developed. Or from wireless to from wired to wireless, or narrowband to the broader bandwidths. But why do we have this issue? What is it that we're missing? Well, from the literature, this underestimation is not expected. We're changing the waveform and the timing of the phones, microalignment time shifts, pitch accuracy. So I put all of these under jitter, some variation in timing. And I also heard what I'm calling power matching, that is, some syllables sound over or under emphasized. That is, the prosody is a bit off. So, an experiment to test the jitter theory. I did this for wideband PESC and VisQual, which already have some ability to deal with variable delay or timing issues. I added more. So right now the picture is, originally the picture is, 32 millisecond frames, for example, with 50% overlap, and frames for the reference speech are paired off with frames for the test speech, and they're compared. I added many more frames on the test speech, so a 2-sample stride, 99 point something % overlap, and an exhaustive search algorithm under some constraints about the width of the search and monotonicity, of course, so that each of these reference frames is paired up with the best test frame, and you can see that allows for much more accommodation of timing variations. And the result was that here are the DNN sources in yellow and non-DNN here. We have to move quickly, but there was a great uptick in these scores for these DNN cases and no change in the score for the non-DNN case. So this is exactly what we need. We're removing jitter and boosting the scores in the one case but not in the other. This would indicate that some nearly inaudible jitter is present, but the full reference estimators are penalizing it much too seriously. The experiment to test the power matching theory is similar, measuring power for the reference and test speech per frame and calculating a per frame correction factor and applying it gives an additional little boost on the scores. And that boost is more significant for the DNN cases and less significant for the non-DNN cases. So again, I believe this indicates that power matching is an issue. So in summary, we've documented the issue more broadly and numerically than previously and seen this consistent underestimation, overestimation, proposed that one can actually combine them, and we show in the paper that we get really good results that way. Also, arguing that with more data, one could train ML-based no-reference estimators to do better on this case. But the bulk of the work here is about this full reference underestimation issue. And again, to be clear, that I'm not pointing out a failure. I'm saying we need to go through another one of these cycles. There's something going on here that our current modeling of human hearing and judgment is not taking account of, or maybe it's taking too much account of it. We're too sensitive to jitter, too sensitive to power mismatches. But very important, what I've done here are demonstrations. They're not proposed fixes. We should not go slap these things into our estimators. We should not remove unlimited amounts or unlimited power fluctuations without some penalty to the score, right? We don't know how much we need to penalize when we do this. Real fixes are fully integrated, optimized, calibrated, tested broadly. So we're providing some information that we hope can lead to that. Thank you very much for your time today.